I mentioned at the end of the last video that while we can always define a double integral over some region in the xy plane as a limit of a double Riemann sum, it's not always going to be practical to evaluate things that way. So I said we were going to have some other techniques. Didn't tell you what they are. That's what we're going to do in this video. Okay. So I've got this specific problem here. So the function I'm integrating, which we still call our integrand, is 3 minus x minus y. Now that's a relatively nice function because that's a linear function. So if z is 3 minus x minus y, that's giving me a plane. Okay. I'm integrating over R, and I've just drawn a picture here of R. It's this rectangle. I want to introduce some notation for rectangular regions. You'll notice that along the x-axis, we've got the interval from 0 to 1. And along the y-axis, we've got the interval from 0 to 2. I can write this as 0, 1, then what looks like the multiplication symbol, 0, 2. This is not a cross product because these are not vectors. These are intervals. This is what we call the Cartesian product. And it's just a nifty way of denoting a rectangle without having to necessarily draw the picture. Okay, so this is all the points where x is anything between 0 and 1, including those endpoints, and y is anything between 0 and 2, including those endpoints. All right, I'd like to draw a picture of the volume that we're going to be calculating. Now, as a general rule, a double integral is signed volume. I just used the word volume. That's because I rigged this problem so that over this rectangle, our heights are always going to be non-negative. So the signed volume in this particular case is the actual geometric volume. Okay, so what I'm going to do is I'm going to first of all just draw my rectangle. So let's see, we're coming out 1 and over 2. So there's my rectangle R on the xy plane in 3 space. Now because this is a plane, if I just draw in the heights that I have at the 4 corners, I can connect those with straight lines, and that'll give me that cross-section of that plane that's essentially determining my ceiling. So at this point, at the origin, x and y are both 0, so we've got the height is 3 minus 0 minus 0. We're going to be up here at a height of 3. At this point, x is 1 and y is 0, so our height is 3 minus 1 is 2. So I'm going to come up a distance of 2. I'm going to go ahead and connect that. I'm sort of just drawing in a wall there. Okay. At this point, x is 0, but y is 2. So we've got 3 minus 0 minus 2. That's going to be 1, so I'll come up a height of 1. And at this point, x is 1 and y is 2, so our height ends up being just 0. So we're actually on the xy plane there. And now if I just connect these points here with straight lines, I can see this is the section of the plane that I'm getting as the top of my surface. Okay, now this corresponds to actual volume because our heights are actually positive. And in first semester calculus, you learned how to calculate some volumes. In particular, you learned the method of slicing. So I'm going to calculate this volume using what I'm going to just call the 3A method of slicing. And then we'll see if we can generalize that and develop the 3C method. Okay. All right, so when we're slicing, we're going through our 4-step process. We're going to chop. Okay. And I'm going to choose to chop this by chopping the things into vertical slices. So I'm going to chop my x interval from 0 to 1 into little pieces like so. Okay. So I'm doing that here. So I'm chopping this rectangle here into these little strips like so. Now, of course, that induces a chopping of the volume into little strips of volume. I'm not going to draw in all of those here, but we'll draw in one of those in just a moment. Okay. Because step 2 is to approximate. So I'm going to try to approximate the volume that I have lying above one of these strips. Okay. And basically what's going to happen is at the back of the strip, I'm going to have some sort of a trapezoid like so. But at the front of the strip, you can see as we move forward, our z values are decreasing. So at the front of the strip, I'm going to have one that's just a little bit smaller. Okay. So the front and the back aren't exactly the same size. Okay. Well, that's annoying. Let's pretend they are. Okay. Because if they were the same, then I could say I can calculate this volume, delta x here, that would be the thickness of the slice. And if the front and the back were exactly the same, and it was just essentially the extrusion of that cross-sectional region, then I could say that the volume was the area of the base, or the cross-sectional area rather, the cross-sectional area times the thickness of the slice. So I'm going to just pick a representative x value and get the cross-sectional area, and then pretend that it's the same. Okay, so I'm going to pick an xi star, a representative x value, and I'm going to calculate the cross-sectional area. So A is my cross-sectional area for that x value. And if I take that and I multiply that by delta x, that's going to give me an approximation of this volume. Of course, then what we do is we add all of those up. So I'm creating a Riemann sum. Let's see, I need some space. I can actually, I think, erase, yeah, I can erase these pictures. Okay, so we get the sum as I goes from 1 to n of A of xi star times delta x, my representative cross-sectional area times delta x, and then, of course, step 4, we take the limit. So we get the limit as n goes to infinity of this Riemann sum. Again, I've chosen to use a regular partition here, not necessary as part of the definition, but simpler to work with. But that then becomes the integral. Now, x was varying, remember, from 0 to 1 for this example, of the cross-sectional area of x with respect to x. Okay, cool. So we're integrating a cross-sectional area, and it's that single integral that we're going to be getting. Okay. Now, this works in 3a, provided that that cross-sectional area is something that we can actually calculate. And it is in this case, because we're getting nice geometric shapes. Okay. So, if I look in a plane, x equals xi star, let's say, okay, that's going to be parallel to the yz plane. Okay. And what I will have is y is going to be going from 0 to 2. And let's calculate what our z values then would be. Now, because z is overall a plane, when I intersect it with this other plane that's parallel to the yz plane, the cross-sectional curve I'm going to see is going to be just a line. Okay. So let's see. At this point, y is 0, but x is xi star. So I'm getting 3 minus xi star would be my height at that point. At this point, I'm taking 3 minus xi star minus 2, so that's going to give me 1 minus xi star. So that's the intersection of the plane z equals 3 minus x minus y with the plane that I get by holding x fixed. So this is my cross-sectional area. And what's nice about that is that's a trapezoid. I can calculate the area of a trapezoid just using formulas from geometry. That's what we needed in 3A, that the cross-sectional areas that we were getting were formulas that we had from geometry. Were shapes where we had a formula for the area of that shape that we could get from geometry. Well, here I can say that means that A at xi star, that area is just going to be this base, which is 2, times the average height. So to get the average, I simply add and divide by 2. So 3 minus xi star plus 1 minus xi star divided by 2. Now, of course, this 2 and this 2 will cancel, and so I'm just getting 4 minus 2 xi star. Fabulous. So that's telling me that this Riemann sum, we were taking the limit as n goes to infinity of the sum as I goes from 1 to n of, we got a formula for this. 4 minus 2 xi star was my cross-sectional area times delta x, but that means I've got a specific integral that I can work with. This is going to be the integral from 0 to 1 of 4 minus 2x dx. Let's actually calculate that. So that's going to be 4x minus x squared evaluated between 1 and 0. So that's 4 minus 1 minus 0, which is just 3. So we would get that the volume is 3. Okay. We just calculated the volume represented by this double integral the 3A way. The 3A way was to do a volume by slicing. So we sliced the x-axis up into little pieces, and we calculated the cross-sectional area that we got at a representative x value. So this was essentially finding that cross-sectional area, and then our integration was multiplying that cross-sectional area by the thickness of the slice, adding them up, and taking the limit. Okay. Let me just remind you what that looked like. When we looked in the plane x equals xi star, which was parallel to the yz plane, we determined that we were getting a trapezoid, like so. Okay. And so we determined that A of x was just the area of that cross-sectional trapezoid that we got. Now, in 3A, we had to get a nice shape because we were relying on being able to calculate that area using a nice formula from geometry. But if we think about it, I know how to find areas of lots of regions that I don't have geometric formulas for. Because I could think of that area as, so this was actually A of xi star, I'm sorry. Okay. I could think of A of xi star as an integral. Okay. This function right here, that was what we got by holding x constant at xi star. So that was f of xi star comma y. Holding x constant, we turned it into a function of one variable, and we were getting this line. Y was going from 0 to 2. I could say this is the integral from 0 to 2 of f of xi star times xi star y dy. I can actually calculate cross-sectional areas as an integral rather than just using a formula from geometry. So the 3C way, we're still doing volumes by slicing. But what we're doing is we're calculating the cross-sectional area as an integral rather than using a geometry formula. So it would be the integral from 0 to 1 dx. I'm just going to write that cross-sectional area function as an integral from 0 to 2 f of xy dy. Now here I just wrote it as f of xy, but when I'm doing this and I'm integrating the inside integral with respect to y, that dy tells me y is my variable. I'm holding x constant. I'm just not plugging in a specific x value as I do when I'm creating the Riemann sum, because I'm of course then going to vary x over all of the x values from 0 to 1. Okay. But this inside integral, we actually call that a partial integral. It's just like a partial derivative. I take my function of two variables, I hold one of the variables constant, and I integrate with respect to the other variable. And so I can do that. That's going to be our 3C method. We've been going for a while here, so I'm going to stop this video here, but we'll actually calculate this. Let's remember that we've gotten 3 when we did it the 3A way. We should get exactly the same thing doing it the 3C way, and we'll get that in the next video.